When a duplex 20 horsepower submersible sewage pump station connected to a permanent standby generator through an automatic transfer switch experiences a current imbalance greater than 10% on the load side of the motor starters under normal utility power, but the imbalance disappears when running on the standby generator, several factors should be considered. Here are possible causes. Firstly, generator voltage regulation could be the issue. The generator might not be regulating voltage as tightly as the utility, which can lead to voltage imbalances on the load side. Secondly, generator frequency regulation needs assessment. Similar to voltage, the generator may not be regulating frequency as tightly as the utility, potentially causing current imbalances in the motors. Thirdly, motor wiring should be inspected. A wiring error in the motor connections could lead to an imbalance when running on utility power. Fourthly, stator winding faults could be present. Faults in the motor stator windings can cause current imbalances under specific operating conditions. Fifthly, dynamic unbalance may be a factor. When running on the generator, the load may be more balanced due to different operating characteristics of the generator compared to the utility. To troubleshoot these issues, follow these steps. 1. Check generator voltage and frequency. Measure the voltage and frequency of the generator output under a load. Compare it to the utility specifications. 2. Inspect motor wiring. Verify the wiring connections for each motor and ensure they are correct. 3. Test motors on both utility and generator power. Swap the motors between the utility and generator power sources to eliminate the possibility of motor faults. 4. Compare motor performance data. Gather motor performance data, including current, power factor, and speed, under both utility and generator power. Analyze the data to identify any significant differences. 5. Consult the manufacturer. Contact the pump and generator manufacturers for their expert opinions and support. Also keep in mind additional considerations. Current imbalance can lead to overheating and premature failure of pump motors. A properly functioning automatic transfer switch should isolate the generator from the utility supply to prevent backfeeding. Regular maintenance of the pump station and standby generator is crucial to ensure optimal performance and prevent issues. Let us consider voltage and frequency regulation. Voltage regulation refers to a generator's ability to maintain a stable voltage output regardless of changes in load. Poor voltage regulation can cause voltage imbalances affecting the current drawn by the motors. Frequency regulation is the generator's ability to maintain a stable frequency output, typically 60 Hz in the United States. Frequency fluctuations can also lead to current imbalances in the motors. When checking these parameters, use a calibrated multimeter and frequency counter. Measure voltage phase to phase and phase to neutral at the generator output terminals under different load conditions. Also, measure the frequency under the same load conditions. Compare these measurements to the generator's specifications. Significant deviations indicate poor regulation. Regarding motor wiring, incorrect or loose wiring connections can cause significant current imbalances. Verify that all motor connections are tight and properly configured according to the motor's wiring diagram. Use a torque wrench to ensure connections are tightened to the specified torque. Look for signs of corrosion or damage to the wiring and connectors. If any are found, clean or replace them. Motor faults can also contribute to current imbalances. Stator winding faults, such as short circuits or open circuits, can cause unequal current draw. Insulation breakdown within the motor can also lead to imbalances. Using an insulation resistance tester, also known as a megometer, measure the insulation resistance between the motor windings and ground. Low insulation resistance indicates a potential winding fault. Perform a motor winding resistance test to check for open or shorted windings. Significant differences in resistance between phases indicate a fault. When testing the motors on both utility and generator power, the goal is to isolate whether the imbalance is related to the power source or the motors themselves. By swapping the motors between the two power sources, one can determine if the imbalance follows the motor or remains with the power source. Gather comprehensive motor performance data under both utility and generator power to identify any significant differences. Measure voltage, current, power factor, and speed for each motor under various load conditions. Use a power quality analyzer to capture detailed data, including harmonics and transient events. Analyze the data to identify patterns or anomalies that could indicate a problem. Contacting the pump and generator manufacturers can provide access to expert opinions and specific recommendations for your equipment. Manufacturers have detailed knowledge of their products and can offer valuable insights into troubleshooting complex issues. Provide them with all the data you have collected, including voltage, frequency, current, and motor performance data. Also, inform them of any recent maintenance or repairs performed on the equipment. When looking at additional considerations, it's crucial to understand the impact of current imbalance on motor lifespan and the importance of proper automatic transfer switch operation. Current imbalance can cause overheating in motor windings, leading to premature insulation breakdown and reduced motor lifespan. Motors operating with significant current imbalance are also more prone to vibration and mechanical stress. A properly functioning automatic transfer switch should isolate the generator from the utility supply to prevent backfeeding, which can damage equipment and endanger personnel. Test the automatic transfer switch regularly to ensure it operates correctly and transfers the load seamlessly between the utility and generator power sources. Regular maintenance of the pump station and standby generator is essential for optimal performance and preventing issues. This includes routine inspections, cleaning, lubrication, and testing of all components. Keep detailed records of all maintenance activities and repairs performed. Now let's dive deeper into the automatic transfer switch. The automatic transfer switch is a critical component in the system, ensuring a seamless transition between utility and generator power. Malfunctions within the automatic transfer switch can contribute to current imbalances or other power quality issues. Inspect the automatic transfer switch contacts for signs of wear, corrosion, or damage. Clean or replace contacts as necessary. Check the automatic transfer switch control wiring for loose connections or damaged insulation. Verify the automatic transfer switch settings are correct and aligned with the system requirements. Test the automatic transfer switch transfer time to ensure it meets the specified performance criteria. The grounding system plays a vital role in maintaining electrical safety and preventing equipment damage. An inadequate or faulty grounding system can contribute to current imbalances and other electrical problems. Inspect the grounding conductors for proper size and connections. Verify the grounding electrode system meets the requirements of the electrical code. Perform a ground impedance test to ensure the grounding system is effective. Ensure all equipment is properly bonded to the grounding system. Harmonics are distortions in the voltage and current waveforms that can cause various problems, including current imbalances, overheating, and equipment malfunction. Nonlinear loads, such as variable frequency drives and electronic devices, are common sources of harmonics. Use a power quality analyzer to measure the harmonic content of the voltage and current waveforms. Install harmonic filters to mitigate the effects of harmonics if necessary. Conduct a load analysis to determine the impact of nonlinear loads on the system. Single phasing occurs when one phase of a three-phase power system is lost, resulting in severe current imbalances and potential damage to motors and other equipment. Single phasing can be caused by blown fuses, open circuit breakers, or damaged wiring. Install single phase protection devices to detect and prevent single phasing conditions. Regularly inspect the electrical system for signs of single phasing, such as unusual motor noise or overheating. Ensure all fuses and circuit breakers are properly sized and maintained. Surge protection devices, also known as transient voltage surge suppressors, are designed to protect electrical equipment from voltage spikes caused by lightning strikes, power surges, and other transient events. Voltage spikes can damage sensitive electronic equipment and contribute to current imbalances. Install surge protection devices at the service entrance and on critical equipment. Inspect surge protection devices regularly to ensure they are functioning properly. Replace surge protection devices that have been damaged or have reached the end of their lifespan. Proper ventilation and cooling are essential for maintaining the temperature of electrical equipment within acceptable limits. Overheating can lead to reduced equipment lifespan, insulation breakdown, and current imbalances. Ensure adequate ventilation around electrical equipment. Clean cooling fans and air filters regularly. Monitor equipment temperatures using thermal imaging or temperature sensors. Install additional cooling measures such as fans or air conditioners if necessary. Power factor correction can improve the efficiency of the electrical system by reducing reactive power and improving voltage regulation. Low power factor can lead to increased current draw, voltage drop, and current imbalances. Install power factor correction capacitors to improve the power factor of the system. Conduct a power factor study to determine the optimal size and location of power factor correction capacitors. Monitor the power factor regularly to ensure it remains within acceptable limits. Insulation resistance testing is a critical maintenance procedure for assessing the condition of electrical insulation in motors, cables, and other equipment. Lower insulation resistance indicates potential insulation breakdown, which can lead to current imbalances, short circuits, and equipment failure. Perform insulation resistance tests on a regular basis using an insulation resistance tester. Compare insulation resistance measurements to previous readings and to manufacturer's specifications. Replace equipment with low insulation resistance to prevent failures. Vibration analysis is a diagnostic technique used to detect and identify mechanical problems in rotating equipment, such as motors, pumps, and generators. Excessive vibration can indicate misalignment, imbalance, bearing problems, or other mechanical issues that can contribute to current imbalances. Perform vibration analysis on a regular basis using a vibration analyzer. Compare vibration measurements to previous readings and to industry standards. Correct any mechanical problems identified through vibration analysis. Thermal imaging, also known as infrared thermography, is a non-contact technique used to detect temperature differences in electrical equipment. Elevated temperatures can indicate loose connections, overloaded circuits, insulation breakdown, or other problems that can lead to current imbalances. Perform thermal imaging surveys on a regular basis using a thermal imaging camera. Identify and correct any hotspots detected during the thermal imaging survey. Regular maintenance of electrical connections is essential for ensuring reliable and safe operation of electrical equipment. Loose, corroded, or damaged connections can cause increased resistance, voltage drop, and current imbalances. Inspect electrical connections on a regular basis. Tighten loose connections using a torque wrench. Clean corroded connections using a wire brush or chemical cleaner. Replace damaged connections with new components. Proper cable management is essential for preventing cable damage, reducing the risk of electrical hazards, and ensuring reliable operation of electrical equipment. Cables that are poorly supported, routed improperly, or exposed to excessive stress can be damaged, leading to short circuits, ground faults, and current imbalances. Ensure cables are properly supported using cable trays, hangers, or clamps. Route cables away from heat sources, sharp edges, and other potential hazards. Avoid overbending or twisting cables. Regularly inspect cables for signs of damage. Proper labeling of electrical equipment and circuits is essential for safety and efficiency. Clear and accurate labeling helps prevent accidental contact with energized parts, facilitates troubleshooting, and ensures that maintenance personnel can quickly identify and locate the correct circuits. Label all electrical equipment and circuits with clear and durable labels. Include information such as voltage, current, and circuit function. Update labels as necessary when changes are made to the electrical system. Safety interlocks are devices that prevent access to energized parts of electrical equipment when the equipment is in operation. Safety interlocks help protect personnel from electrical shock and arc flash hazards. Install safety interlocks on all electrical equipment that contains energized parts. Regularly inspect safety interlocks to ensure they are functioning properly. Never bypass or disable safety interlocks. Arc flash is a dangerous electrical hazard that can occur when a short circuit or other fault causes a sudden release of electrical energy. Arc flash events can result in severe burns, injuries, and fatalities. Conduct an arc flash hazard analysis to determine the potential arc flash hazards in the electrical system. Implement arc flash protection measures, such as using arc-rated personal protective equipment, installing arc flash relays, and reducing fault clearing times. Provide arc flash training to all personnel who work on or near electrical equipment. Electrical safety training is essential for ensuring that personnel who work on or near electrical equipment are aware of the hazards and know how to work safely. Electrical safety training should cover topics such as electrical hazards, safe work practices, personal protective equipment, and emergency procedures. Provide regular electrical safety training to all personnel who work on or near electrical equipment. Keep records of all electrical safety training. Emergency procedures should be in place to address electrical emergencies such as electrical shocks, fires, and arc flash events. Emergency procedures should include instructions for de-energizing equipment, providing first aid, and contacting emergency services. Post-emergency procedures in a conspicuous location. Conduct regular emergency drills to ensure that personnel are familiar with the procedures. Lockout/tagout procedures are used to de-energize electrical equipment before it is worked on. Lockout/tagout procedures help prevent accidental energization of equipment, which can cause electrical shock or other injuries. Develop and implement lockout/tagout procedures for all electrical equipment. Train personnel on the proper use of lockout/tagout procedures. Use lockout/tagout devices to secure equipment in the de-energized state. Regular inspections of electrical equipment are essential for identifying potential problems before they lead to failures. Inspections should include visual inspections, electrical testing, and mechanical testing. Perform regular inspections of electrical equipment. Document all inspection findings. Correct any problems identified during inspections. Proper documentation of electrical equipment and systems is essential for troubleshooting, maintenance, and future upgrades. Documentation should include wiring diagrams, equipment specifications, maintenance records, and inspection reports. Maintain accurate and up-to-date documentation of all electrical equipment and systems. Store documentation in a safe and accessible location. Review documentation regularly to ensure it is accurate and complete. When dealing with submersible sewage pumps, there are additional considerations to keep in mind. Submersible pumps are designed to operate submerged in water or sewage. Special precautions must be taken to ensure that the pumps are properly sealed and protected from corrosion. Inspect submersible pumps regularly for leaks or other signs of damage. Use submersible cables and connectors that are designed for use in wet environments. Ground submersible pumps properly to prevent electrical shock hazards. Variable frequency drives are often used to control the speed of submersible pumps. Variable frequency drives can improve energy efficiency and reduce wear and tear on the pumps. Ensure that variable frequency drives are properly installed and configured. Monitor the performance of variable frequency drives regularly. Backup power systems, such as generators or uninterruptible power supplies, are often used to provide power to submersible pumps during power outages. Backup power systems help ensure that sewage continues to be pumped even when utility power is lost. Ensure that backup power systems are properly sized and maintained. Test backup power systems regularly to ensure they are functioning properly. Remote monitoring systems can be used to monitor the performance of submersible pumps and other equipment from a remote location. Remote monitoring systems can help detect problems early and prevent costly repairs. Install remote monitoring systems on critical equipment. Configure remote monitoring systems to send alerts when problems are detected. Monitor remote monitoring system data regularly. Finally, consider the specific regulations and codes that apply to electrical systems in your area. Electrical codes, such as the National Electrical Code, provide detailed requirements for the safe installation and operation of electrical equipment. Comply with all applicable electrical codes and regulations. Consult with a qualified electrical contractor to ensure that your electrical system meets all applicable requirements. By addressing these possible causes and implementing the recommended troubleshooting steps, you can effectively diagnose and resolve current imbalance issues in a duplex sewage pump system, ensuring reliable and efficient operation. Regular maintenance, adherence to safety protocols, and expert consultation are key to preventing future problems and prolonging the lifespan of the equipment.